So before I introduce our lecturer, let me ask you all to mute your microphone. I can do that as a host, but it's easier if you do yourself. And question will be allowed only at the end. So at the end, you can either raise your hand or ask the question in the chat. But to do so, you have to make your name recognizable on the chat. Some of your names are completely unrecognizable, so you can rename yourself if you want to. And I think that's it in terms of logistics. Right, so welcome everyone to the last Kavli lecture of this academic year, and also which is also the very first Kavli lecture online. And we are very glad to have Stephen Smartt, who has kindly agreed and accepted to give his lecture online with, under these the current circumstances. So Stephen is a professor of astrophysics and director of the Astrophysics Research Center at Queen's University in Belfast. And he has had other previous positions, and I don't have time to list them all. But I just want to mention that he was also in Cambridge, where he was here as a postdoc and the UK PPARC Advanced Fellow at the IoA. So he's, I think you have been here for 5 years, it was sort of, yeah. So it's many of you know him. I mean, when he was here. Besides, of course, his research. So he has been given a lengthy list of awards and honors, which I don't have time to list them all, but I just do wish to congratulate with him that this year has been elected Fellow of the Royal Society. And he has been leading or co-leading several major international projects and observing programs aimed at detecting and characterizing supernovae and transients, such as the famous PESTO-ESO public spectroscopic surveys of transient objects. He is UK project scientist for LSST, science lead of for PanSTARRS-2 of the transient survey, and also, for instance, science leader of the NASA Atlas project, just to name a few projects. Is well known, one of the major experts in the area of supernovae and more general transients. And among the recent achievements, this has been the famous follow-up of the electromagnetic counterpart of the 2017 gravitational wave event resulting from the merging of two neutron stars, where his team has identified the production of heavy radioactive elements, as confirming the kilonova models. So these are some of the topics that he will be covering, I guess, today in his lecture today. And so, Stephen, when you're ready, you can start.
Thanks, Roberto. Okay, let me share my screen. Okay, can you see my screen okay? With the title slide?
Yes, yep.
Just let me check before I start. Can you see a change in the title of the slide when I click here? Just let me do that before I start.
Yeah. Mm-hmm.
Yeah. Okay, so thank you, Roberto, for the introduction, and thank you for the invitation to give this Kavli lecture. Just a pity it's online. I look forward in the future, I hope, to having a visit associated with the lecture. Not quite the same here, not having tea at 3:30 and standing up in the Sackler, of course. But I hope I can make the trip soon. Okay, so here's an outline of what I'll talk about. To start with, I'm going to give you 2 stories of forgotten physics separated by 100 years. Which are sort of interesting stories, but have some implications in the context and content of what I'll talk about. And then I'll mostly talk about the diversity of stellar explosions and actually stellar mergers that we've found from wide field surveys. So when we scan the sky, and we are now close to being able, that by the end of the year, I think by the middle of next year, we will have facilities that can scan the sky every night, multiple times a night to 20th magnitude. And there are a combination of facilities that will do that even before LSST comes along and goes much deeper. But as we scan the sky every night, we find transients. The three physical questions we want to answer are: what is the power source of these objects? What is powering the luminosity? How much mass is ejected? And what is the chemical composition? And then answering those then gives us a method to try and look for common mechanisms that produce the transient sky. And we're seeing a vast diversity now in stellar explosions, not just the normal type 1a supernova and type 2s from core collapse, but a wide diversity in the type of objects that produce transients. And I'll focus on fast transients and kilonova in particular, because that's what we're working on mostly. My group is working on mostly, and that's related to multi-mesh classic physics, linking gravitational wave detections with photons. And so in the context of the history of transient objects, usually when I'm in a lecture theater, and I've done this before, and I've asked the question, what astronomical event connects these two images? Only one person has got it right, or nearly right, almost right. I follow Mazzali. I'll give him the credit for being right. So can you think of? I'm sure you can recognize these two objects or these two images. So what astronomical event links both of these, and what is the link? I'll give you a few seconds just to think about it. I won't ask a question, try and take answers now, but usually when I'm in a lecture theater, I get a range of answers. So the answer is, so this is M31, of course, on the island of Ireland. So the astronomical event that connects them is the nova in the Andromeda galaxy. So this was originally credited to the discovery by Ernst Hartwig, based in Tartu on the 20th of August in 1885. He found a new object associated with this nebula, the Andromeda Nebula. At the time, of course, no one recognized the implications and importance of this event because the distance to Andromeda wasn't known. And so even when Hubble came along and measured the distance to Andromeda, it was still another 20 years. Sort of 10 to 20 years before Zwicky and Bader realized, well, if Hubble is right, and if the distance to Andromeda is about a megaparsec or so, then this nova that was found in the Andromeda galaxy is not like any nova that we know of in the Milky Way. If Hubble's distance is right, then this nova is actually about 2 times 10 to the 9 solar velocities. That's about 10,000 times brighter than the most luminous star in our galaxy, or the nova that we frequently detect in our galaxy. And so just with that measurement, Bader and Zwicky, just with the measurement of distance and the magnitude that Hartwig recorded, actually was a reasonable light curve for the object. With the luminosity then, they suggested that this 10 to the 9 solar luminosities that was produced physically came from the collapse of a massive star, the collapse of the core of a massive star, and it was the gravitational release, the potential energy released when the core collapsed that produced the luminosity in some way, and that an object of, effectively they described a neutron star, and remember this was only 2 years after the neutron was detected, 30 years before pulsars were detected. They suggested that when the core collapsed, it formed an object of density similar to an atomic nucleus, and that potentially this was the source of high-energy cosmic rays. So great physical foresight just from 2 measurements of the magnitude of the peak brightness of the object and the distance to the galaxy. So what links, and that was the start of extragalactic supernova studies. But what links these two is that actually it was Isaac Ward who discovered this event on the 19th of August, 1885 from Belfast. And so there's written records of Isaac Ward, who wasn't a well-equipped amateur astronomer in Belfast at the time. He had traced the moons of Jupiter and made various other precise astronomical measurements. And so he recorded this discovery a day before Ernest Hartwig, but unfortunately he didn't tell anyone before Ernest Hartwig. So Hartwig does get the credit, but Isaac Ward is now being credited. So you could say that the study of extragalactic supernovae started in Belfast in 1885. Unfortunately, that was the golden period of supernova studies, because the next one discovered from the island of Ireland was not until 2010. So we have discovered thousands of supernovae, but none of them with a telescope that is based on the island of Ireland. And so the next one, to my knowledge, the next supernova discovered after 1885 was by Dave Grennan in 2010. So a little bit of a gap. So let me just give you an overview of the normal supernovae that we find, the majority of supernovae that we see, and then we'll talk about the more extreme merger events that we've detected. Type 1a supernovae, thermonuclear supernovae, as you know, come from white dwarf explosions of white dwarfs, either in a binary involving a main sequence companion or red giant companion, or in a double white dwarf merger. And in both cases, you produce a white dwarf which is close to or just over the Chandrasekhar limit, which then explodes and burns the carbon and oxygen to heavier elements. Now, as this explosion happens rapidly, the ashes from the carbon and oxygen burning have to preserve the proton to neutron ratio. So the elements produced are typically magnesium, silicon, sulfur, calcium, and also importantly, nickel-56. So nickel-56, 28 protons, 28 neutrons. So these supernovae do not immediately produce the stable iron in the universe. They can only produce, as they burn through the iron group elements, nickel-56 because of this constraint to preserve the proton to neutron ratio. Radioactive nickel-56 is the element which is produced in large quantities. About half the total mass of the white dwarf is burned to nickel-56. So this between half and 0.7 of a solar mass or so is what produces the luminosity in a type 1a supernova. The nickel-56 decays to cobalt-56 either through electron capture and emission of a neutrino and a gamma ray, and the half-life of that is 6.1 days. The cobalt-56 then decays to iron-56, stable iron, again two processes, either electron capture or positron emission. And that's got a half-life of 77 days. And the combination of those two timescales are what it produces in combination with the solar mass, 1.4 solar masses or so ejected. The combination of those produce the characteristic type 1a light curves that we see. So the lifetime of radioactive nickel-56, the half-life of 6 days, defines the rise time of type 1a supernovae in combination with the 1.4 solar mass of ejecta and the diffusion timescale that implies for the photons to diffuse out. And then the type 1a supernovae and others have a longer tail, which is driven by the decay of cobalt-56 to stable iron. So that sets the characteristic light curves that we see for type 1a. But it's nickel-56 which is the key powering source for all type 1a supernovae and most hydrogen-free supernovae as well, even the 1b's and 1c's. The standard paradigm for type 2 supernovae, type 2, type 1b, and 1c, is that we have a massive star which has, in its core collapses. So when it reaches silicon burning, it produces an iron core, and that iron core again is about the Chandrasekhar limit, about 1.4 solar masses. That can't support itself or the star anymore, and the core collapses at the end of silicon burning when an iron core is produced. So remember, if you just look at this cartoon picture of red supergiants, the sun is shown here increased in radius by a factor of 10. What actually collapses in the star is obviously not the star itself, it's the core of the star, it's the iron core which collapses, and the iron core is only about the size of the Earth. So the iron core collapses from 6,000 kilometers down to about a neutron star radius of 10 kilometers or so. And it's that gravitational potential energy release of 10 to the 53 ergs that drives a shock wave through the star. The shock wave is invigorated in some way by the neutrino emission, which is given off. Most of that 10 to the 53 ergs comes out in neutrino. About 1% of that neutrino energy is captured, and we see explosions with kinetic energies of 10 to the 51. So that's the standard paradigm for core collapse supernovae. Their early light curves are determined by the structure of the star before it collapses. So in this picture, a red supergiant, when it explodes, will produce a supernova that's quite different to a blue supergiant, a compact blue supergiant. You can see a blue supergiant like the one that produced 1987A is shown in the left corner here. And just the radius is much smaller, and a very different density profile. So as the shock wave goes through the star, the early stages are quite different. But it's the same explosion mechanism, and it's only the core that collapses in the first instance. And if you look at the light curve here of the two type 2 supernovae, one is 1987A with the rise to peak of about 60 to 100 days. The other one is a classic type 2P supernova, which has a plateau in its light curve for a period of 100 days. So the 1987A event came from a blue supergiant. The red line comes from a red supergiant. And that just shows you that the early stages are determined by the radius and density of the star. That's what dictates the appearance of the explosion. But at late stages, they've settled onto the cobalt decay tail. So radioactive nickel is produced in these as well, but by a factor of about 10 less. The mass of nickel 56 is about a factor of 10 less in core collapse, in most core collapse compared to type 1A supernovae. And so they've got fainter tail phases, but we still see this characteristic decline where it's not nickel by 100 days, of course, all the nickel is gone, but this is cobalt, which remains, which decays to stable iron 56. And that drives the late stages of the evolution of the supernovae. Let me show you, this is the other story of forgotten physics, which was forgotten for about 20 years or so. There was a paper published, so this is implication. So I just told the two slides there are just to give you an idea of the standard paradigms for type 1A and what type 1 supernovae and core collapse within stars. But when these wide field surveys started several years, then the diversity of stellar explosions forced people to think of what really are the explosion mechanisms behind the different objects that we were finding. And in 1982, Dave Arnett published a paper on analytic solutions for the early part of the light curve for type 1 supernovae. And you can see the citation history of this paper. So from 1982 until 2007 or so, pretty flat. There's somewhere between 2 and 10 citations a year. And then suddenly in 2007, it rocketed. So this is a theoretical paper just explaining how a compact star, when it explodes, how it would expand and what the light curve would look like if it was powered typically by radioactive nickel 56. So around 2007, the citations that this exploded and the paper became much more widely recognized. And so again, usually when I'm in a lecture room, I ask what was the reason for this happening. And the reason is the explosion in wide field time domain surveys that happened around that time, 2008, 2009. Started with PTF, pan stars originally, and PTF then became ZTF, of course, PESTO survey, dark energy survey, and even smaller facilities like Assassin and Atlas, which are of order 50 to over 100 square degrees, smaller apertures, but capable of serving the sky quicker than the larger facilities, and hence probing the local volume. And so what happened then was that we found this diagram here shows just plots characteristic timescale versus peak luminosity of various transients. And in the gray areas are the standard objects that we knew of up until about 2000 to 2010. Standard core collapse supernovae, thermonuclear type 1a supernovae, and that little strip there, a type peak luminosity range, which what makes them useful for cosmology, of course. And then the classical nova band below that. But since then, these wide field surveys have found a very large diversity in transients, which are by volume, they are rarer than the normal objects that we've studied for half a century or so. So these surveys found very luminous supernovae, 100 times more luminous than standard core collapse. They look like they're associated with massive stars, but 100 times more luminous than typical core collapse. They found these intermediate luminosity transients sitting in the gap between nova and supernovae, and then these faster evolving transients, which are called, there are three names here for various reasons, but they're alternatively called calcium-rich transients, gap transient, just because they're in the luminosity gap, or dot 1A explosions, and the dot stands for 0.1, a tenth of the luminosity and a tenth of the time scale of a type 1A supernova. And then there were these relativistic explosions in the top left, which are really GRB afterglows. So there was a drive then, the experimental side then drove a desire to understand this diagram and physically understand what is going on here. And then this was revolutionized with the discovery of the first kilonova associated with a gravitational wave. And if you plotted it on this diagram of where we expect other kilonova to lie, they're faint and they're fast declining. So they'll be in this region of the diagram here. So the diagram originally came from PTF group, and many others have contributed to it since. So what's physically driving this is that, whoops, sorry, I expected two little arrows to come up there, which have not come up on my screen, sorry. And so what's physically driving this, so I'll just talk you through it, is that the x-axis is being driven by the mass of the object, the ejecta mass, and the y-axis is being driven by the powering source. And so the experimentalists and the theorists, as we discovered this diversity, went back to Dave Arnett's paper, and this is where the Dave Arnett's paper was came back into fashion, and people realized the usefulness of what he had done. And it's a framework just to simply describe the physics of an exploding object with an arbitrary power source and allowing the mass and the explosion energy to vary. And it was trying to understand that diagram, which reinvigorated the interest in this paper. So Dave Arnett's paper, if you go and look at it, it starts with the first law of thermodynamics. Internal energy plus work done equals the heat flow or energy flow in or out of the system. You differentiate that, and you get du by dt plus p dv by dt equals the luminosity of the object, which has got a negative sign because it radiates, and plus the powering source. So this epsilon is the powering source of the explosion. So it could be radioactive nickel 56, but this framework allowed us to put in any arbitrary powering source and to solve these fairly simple equations and come up with an analytic solution for the luminosity of these objects. So if you take a homologously expanding ejecta with a certain mass, expansion velocity, opacity, which of course depends on the chemical composition, and some power source function, which might be an exponential for radioactive decay or something else, which I'll discuss. Then you can solve these equations. Arnett solved these equations to show that the luminosity can be explained by this fairly simple integral. And the key point here is in this, you've got the power source function, which can be arbitrary. And so you can come up with a luminosity as a function of time. And the tau m here is the time scale for the light curve, so the typical time scale, and that's either typically the time it takes to rise to peak. That depends on on the time it takes for the photons to diffuse out of the expanding remnant. So it's dependent on the opacity, the mass, and the velocity, kappa m over v to the half power. And so something which is more massive has a longer time scale, something which which expands fast, then the time scale goes down. If it's got a high opacity, then obviously the time scale goes up. So tau m is measurable. If we have a good light curve, then tau m is measurable. And so we can measure velocity as well from the spectra, which I'll show. We can have a reasonable guess at the opacity from the chemical composition. And so we can estimate the mass of the ejected remnant. So that diagram then, just to emphasize that the x-axis, the diversity in the x-axis is driven by ejecta mass. So longer-lived transients typically have more mass. It takes longer for the photons to diffuse out. And then the peak luminosity is determined really by the powering source. So let me give you one example before I talk about kilonova and stellar mergers. So one example where this was applied and this idea of separating out the power source from the mass with the simple Arnett relations is that these superluminous supernovae, which were in that in the top right-hand corner of the diagram, longer lived than normal supernovae, factor of 100 brighter than typical core collapse supernovae. These were discovered in 2010, 2011. So PTF, there have been a few of these objects which had an unknown redshift and therefore unknown nature. And so PTF, Robert Quimby in particular, this was really the first paper that identified the class and defined the class. And so, so what he did was he spotted that in some of these, they had weak absorption lines, and he associated those with the magnesium-2 2800 resonance doublet from the interstellar medium in the host galaxy. And he was able to determine the redshifts of a sample of about 5 of these, and then link the broad absorption lines to transitions in the UV. The absorption lines in the spectra were not identified at the time, and so the spectra themselves were not well matched to normal supernovae. So this is effectively what he did. Got a redshift, gives you a distance, had a measured apparent magnitude, worked out the luminosity, and these are 100 times, found these were 100 times brighter than the normal supernovae. So the difficulty was they were either their galaxies were unidentified or they were very faint, so it wasn't easy to get a redshift from the host galaxy. And it was only in the very early blue spectra that were able to pick up these the rest frame UV continuum and get the magnesium-2 absorptions. So within about six months to a year, this class was completely defined by PTF and by PanSTARRS. So we had found them out to a redshift of 1, and we showed that their chemical composition then, as you map them over a period of time, the composition looks similar to type 1c supernovae. So these look like carbon-oxygen, massive carbon-oxygen cores which have collapsed, Wolf-Rayet-like stars, either the cores of massive stars within binary systems where the hydrogen has been stripped off, or Wolf-Rayet type stars. That's what the composition of the material looked like, similar to 1c supernovae. But they were initially very hot and very blue, which caused problems in identifying the lines. So you can see the light curve here in the top plot of these. So a normal type 1c supernova is in blue. 98 BW, the first supernova associated with gamma ray burst, is in green. And then all of these bright superluminous supernovas sit above those two. Their light curves are broader. They're significantly brighter. The fact their light curves are broader just must mean they've got a larger ejecta mass than normal type 1c supernova. And the key thing is their peak luminosities could not be powered by nickel 56. So the standard paradigm of powering type 1c supernovae, type 1as, even most core collapse supernovae, this was not capable of describing the peak luminosity of these objects. The tail phases are close to cobalt 56, but we can't get a physical solution to explain the peak plus the cobalt plus the tail phase just with radioactive nickel 56. So some other powering mechanism was needed to explain these. And this the most successful so far. So there's been several several ideas and several models. I think the most successful and the one which explains most of the objects in this class is to have some sort of central engine powering. Now, I'm going to call it magnetar powering because there is a plausible physical mechanism that can create an input power source, which then, when you combine it with the Arnett equation or other more sophisticated light curve simulations, then does reproduce the luminosity that we see. So this goes back to the idea of having a rapidly rotating neutron star, which has got a high magnetic field. Actually goes back to the 1970s. Gunnar and Ostraker proposed that supernova remnants in our galaxy can be the kinematics that we see now in the old remnants can be explained by energy injection from rapidly rotating pulsars or neutron stars in the remnants. So in this case, so it's the same idea here. We've got a rapidly rotating neutron star, so that has rotational energy, just given by a moment of inertia, omega squared over 2. And if you express that in terms of the period where p is in 10 units of 10 milliseconds, then 2 times 10 to the 50 times p to the minus 2, where p is 10 milliseconds. So there's a significant amount. If we have neutron stars which were rotating at of order a few milliseconds, then there's around 10 to the 51 ergs of energy available in that rotating object. And if they have a large magnetic field, around 10 to the 14 Gauss, then they will spin down. If the magnetic field axis is misaligned with the rotation axis, then they'll spin down due to magnetic dipole radiation, and they'll have the luminosity of that spinning down magnetar is given by this formula, and it's dependent, of course, on the magnetic field and the rotation rate, but it is 1 over t squared. So just putting in this, so this Kaysen and Bilstein, Stan Worsley, and Luc Desart came up with this idea around the time that these superluminous supernovae were found, and suggest this was a central energy source that could power the events. And so we, in 2013 and around between those few years since 2010 up to 2015, we and others applied this simple idea to the light curves of the observed luminosity, photometric luminosity light curves of these superluminous events, and found that this produced quite reasonable light curves and matched the events quite well. Some of them have unusual features in the light curves, which might be material which is sitting around this object. But the first order, we can reproduce the luminosity that we see with this idea of rotating neutron stars. There have been alternative explanations, such as interaction with the circumstellar medium, a dense circumstellar medium, but requires quite a contrived type configuration for the progenitor star. Accretion on the central black hole rather than powering through a magnetar can also work, but there are issues with how long that the time scale for accretion can continue. But this is an example of using the simple Arnett formula with a powering source to reproduce, to understand the diversity in the light curves that we're seeing. And so more sophisticated hydrodynamic simulations have supported this idea that these can be powered by central magnetars. The other thing that would become quite popular in recent years is using radiative transfer models to apply to supernova spectra. So what I've shown you here up to now is really just trying to understand the light curves and the luminosity of these events. But of course, what we also want to understand is what they're made of. What is the chemical composition of these extreme objects, of the diversity of objects that we see? Does that give us a clue to the progenitor systems? Does it help in understanding how they may contribute to chemical enrichment? And so the only way to do that is to understand the spectra. So trying to model supernova spectra, of course, is much difficult than for stars. not less, at least because the physics is a bit more difficult, but just empirically, it's difficult to identify which transitions are contributing to the features, because the velocities are so high, and so the transitions get blended together. So here's an example for a high energy type 1c supernova. You can see many of the lines here that are identified are the features are broad. They're typically 10 to 20,000 kilometers per second in width. The features that are identified are usually the strongest features at that wavelength that we expect for a plasma temperature, which is estimated from the overall spectral energy distribution. And so there have been Monte Carlo methods developed going way back to the 90s. Leon Lucy and collaborators developed Monte Carlo methods to reproduce the model spectra of space. We use one written by my colleague Stuart Sim and Wolfgang Kersendorf, and Stuart is also in Belfast. It's a code called TARDIS. There are other codes which are more sophisticated, but this one, if you look at the little cartoon diagram, this gives you, we set up a model which would have layers of different compositions. And these are chosen perhaps with input from a progenitor star and the endpoints of stellar evolution. Monte Carlo radiation packets are set off in the core, which you can see here in gray. And so what happens in this TARDIS simulation is the object expands, we let these radiation packets then diffuse through the expanding supernova, and they emerge, and that gives us the spectrum. So this is the code which is being written it has many approximations. It's typically used in LTE. It's 1D. There's a black body spectrum at the base of the photosphere. But the advantage of using this one is that it's quite fast, and that users can then calculate hundreds or thousands, typically dozens to hundreds of models, varying the input composition, the density profile, and the velocity profile of the material. And so that has given quite good results, particularly for line identification, but also for estimating the expansion velocities of the transients. So that's also fundamental now to what we do. While we do want to understand the overall ejecta mass and the powering mechanism, we also want to understand what is the chemical composition of these transients. So I'll talk a little bit more about applications of this to unusual transients. So all of this, while we find this diversity of transients in optical and near-infrared studies, this was, and we expected to find low-mass objects which evolved very quickly. This was revolutionary, of course, in 2017 when EW170817 was found. There was a weak short GRB found 1.7 seconds later in the same region of sky. In the bottom figure here, you can see the LIGO frequency time diagram. So that's the time before merger of this neutron star binary system. And the signal stretches out to a few tens of seconds. And this is the frequency of the system as it approaches merger. So when this was detected back in August 2017, then, and of course this was LIGO's first very long signal. The binary black holes have typical signals of around, in the LIGO frequency band, of around a few tenths of a second. This is the first object that we found which was loud and lasted tens of seconds. And so just within 11 hours, then the optical counterpart to the gravitational wave source was identified by 6 or 7 telescopes in Chile. Pretty easy to identify. The sky region for this was around 30 square degrees. Distance to the estimated distance of the gravitational wave source was 40 megaparsecs. So just compiling a list of galaxies within 30 square degrees at a distance limit of 40 megaparsecs. This galaxy, NGC 4993, is about number 4 on the luminosity list. So The big telescopes in Chile, DECAM and Vista, got it, obviously detected it early, but the other telescopes are 0.5 to 1 meter, easily picked up this 17.5 magnitude source. So this was the kilonova associated with two merging neutron stars. They had long been predicted to be strong emitters of electromagnetic radiation in the optical near infrared, stretching back to Lee and Kinsinski in around 98, and even before that. And this is a simulation by Stephen Smartt of two merging neutron stars, which is showing you expect to see quite significant ejector mass. And so how they may appear in the optical near infrared depends on the total amount, which is total amount of mass ejected, and exactly what it's made of. We knew this was unprecedented, so the reason, as soon as we detected this probably within 24 hours, the first spectrum and how the object evolved within 24 hours, really convinced us at the time that it was something very unusual. And so we'll just show you a simple light curve here to show you how different this is, this transient was to normal supernova. So in pink is a normal supernova with about a solar mass of ejecta, 1 to 2 solar masses of ejecta. That's a relatively low mass type 1c supernova, relatively fast. That's what we would call a relatively fast evolving object. And in blue is 2017 GFO. That's the label we gave to the electromagnetic transient associated with the gravitational wave source. That's in blue, and you can see that plummets after 5 days. It goes down to 4 magnitudes in 5 days. So even after a day, we saw the decline, the rapid decline of this object, even faster than foreground CVs. And so we knew this was something quite different. So just interpreting that, the fact that it declined rapidly, again, within the simple framework of the Ornette model, if you have the luminosity is given by this fairly simple integral, and the powering mechanism, if you put in a powering mechanism, which is just an analytic function, t to the minus beta, beta is predicted to be between about 1 and 1.3 for the R process, for the radioactive decay of the R process elements. It's not an exponential because you've got to add up lots of decays, which are all individually exponentials, and it can be approximated to a power law. And so if you put in that power law and you put in a time scale where that m is very small, because you expect a small amount of ejecta mass from two merging neutron stars of order about 0.01 to 0.03 of a solar mass. So then the luminosity can be explained quite well with a low ejecta mass, this powering source, which is t to the minus 1.3 or so, and a high velocity. And the velocity, you need the velocity to be high, about 0.1 to 0.2 c in the early phases, because you've got to get a luminosity of, here in absolute mag terms, minus 16, sort of 10 to the 41 ergs. And you've got to get to that luminosity within 11 hours. There's an 11-hour gap between the gravitational wave detection and the peak luminosity of this object. So you need a small mass, high velocity, and then a powering source with this power law. So that worked out quite well. The luminosity you can see here. So if you look on the left is a movie of I hope you can see it, is a movie of a blue source pops up, and then it turns red, as you'll be able to see. It's just top left of the host galaxy. So that's the kilonova fading away. On the right is the light curve with a simple Ornette type model fit. And various other people have done. There've been many light curve plots and fits to this to the luminosity of the kilonova. But the first order, everyone finds that it's got to be about 0.02 to 0.03 solar masses of ejecta. The velocity of it is about 0.2 c. There's arguments over what the opacity of the material is and whether or not there's a blue component or a red component, both. But the powering source has to be t to the minus 1.3 or so. And so that's quite good, quite strong evidence that this is that's the radioactive decay of the R process elements that's producing this luminosity. So to try and identify which elements, so that gives you a broad idea of of the physical characteristics of the kilonova, to get an idea of what exactly, or pin down exactly which elements are powering the event is more difficult. If we're thinking that we understand that mostly the production of the elements up to the iron group from the bulk of the supernova population that we understand in the local universe. So then where do we start if we're looking at the R process elements to try and identify individual events? And one place that people typically started was to look at the peaks in the abundance distribution. So this shows you the relative abundances in the solar system and the abundance peaks that we are familiar with. The R process elements have been labeled as having these first, second, third peaks. And so that's a reasonable place to start. The most abundant elements that we see in the solar system and in the galaxy, and even metal poor stars, which reproduce the solar system abundances quite well. So looking at the most common elements is a reasonable place to start to see if we can identify the elements in the spectrum. So there were a sequence of very good spectra taken over the first 10 days. There's still there's still an ongoing debate about which elements, if any, have been definitively identified in the spectrum. There's two broad schools of thought and ways of analyzing the spectra. One is that it's just really dominated by one component, which, because the early spectra are quite blue, it has to be a fairly low opacity, a material with fairly low opacity overall. And then a second, there are reasonable physical arguments that the kilonova should have multiple components, 2 components in fact, and that one of these should be dominated by the heavier R process elements and another component dominated by the lighter elements. And that's what you may have heard people talking about, the blue and the red component of this event. It's not clear whether or not it's not necessary to invoke a blue and a red component to explain the overall light curve and the luminosity. It may not be necessary to explain the spectra, although that's still to be debated. So one on the right shows, for example, the green line is the observed spectrum, and this is 2 of Dan Cason's models of a blue kilonova with a composition dominated by the light R process elements and a red component dominated by the heavier R process elements, the lanthanides. And if you add them together, you get a reasonable agreement between the overall spectral energy distributions. And so the argument there is the features, many of the features in the spectra are actually from the addition of these 2 SEDs and not individual features due to certain elements. Alternative to that, at the time we proposed some of these features early on in the spectra, particularly the ones you can see here at around 8,000 angstroms, were due to the lighter R process elements, and these were specific. This was specific absorption due to those. And Dara Watson had a Nature paper recently claiming that this region here around 8,000 angstroms is actually strontium-2 absorption, and that you can see it in the first 4 spectra. So the jury's still out on both of these on this argument. So we've been doing exploring this in more detail with the TARDIS code, and a student of ours, James Gillanders, has been working on it. And it was a pretty good, so, just picking strontium out here and saying, well, here's the explanation for the features in the early spectra. It's physically well motivated in that strontium sits under calcium in the periodic table. It's in group 2. The outer electronic structure are therefore similar. And we all know the calcium H and K lines, which are strong, obviously, in many astrophysical systems. And they are linked to the near-infrared triplet, which is also strong. So the calcium lines the H and K lines are ground state transitions, and they are linked to the near-infrared triplet, which we see in many stars and transient objects as well. And then also linked to the forbidden doublet. So strontium-2 has exactly has a parallel atomic structure, where it's got resonance lines at 408 and 422 nanometers, and it has the equivalent of the near-infrared triplet. So what Dara Watson and collaborators proposed, that it was the near-infrared triplet, the absorption from the near-infrared triplet of strontium-2, which was creating those features, which is quite a plausible explanation. So we've been working on this over the last few months with the TARDIS code, and my student James Galanders and Stuart Sim have been working on this to try and see if we can get a consistent. So we tried, rather than just picking individual elements and seeing if they work, what we have tried to do is, or what we are doing is taking the abundance ratios of which come from nuclear networks that are calculated for neutron star mergers, or the physical conditions associated appropriate for neutron star mergers. So those give a fixed relative abundances ratios of the heavy elements, and we take those relative abundances, use some of the new atomic data that's been released, and collaborators in Queens are also calculating some new atomic data for the very heavy elements, which are not yet included, but that's our plan to include. And so we try to reproduce the spectra, but not just one, but then all of the spectra over the first 10 days. So we can get reasonable agreement with this feature again at around 8,000. It looks like that is likely to be dominated by strontium, but there are other components, particularly yttrium and zirconium, have features around that wavelength as well. We're not finding agreement in the blue. There's too much absorption by the same elements in the blue, and so we're trying to work out whether or not that is a serious problem for fitting this with a composition which is dominated by the light elements. Whether or not the fact if you want that absorption around 8,000 angstroms, that clear feature that we see here around 8,000 angstroms, whether or not that implies that you have to have this. You can see the disagreement here between the black and the red. The red's the model, the black is the observation, and so the strontium and these other lines from yttrium and zirconium also cause this significant depression in the blue. So we've got quite a bit to do here, and so I think the conclusion here is that there still isn't a unique explanation for the composition of this object, and it's not clear whether or not it really is two components, a red and a blue, or that it's dominated by one, and in each case, which is actually the most, which is in each case, which is the more, which element actually dominates, or which elements dominate. So I think there's still quite a bit to do there. And so here, I think the questions which are still open is this really separate blue and red components? Can we get physical consistency between the nuclear isotopes that are predicted from these simulations? Do they power the light curve in the way that we require? And including new atomic data, can we get a consistent solution? And of course, I imagine what you want to ask is, well, what is the rate of these kilonova? This is one from 2007. What has LIGO Virgo done since? Well, let me summarize just perhaps slightly disappointing from, I think it's been a very successful run for LIGO Virgo. Slightly disappointing from the electromagnetic perspective, but we haven't got another counterpart. These are just 6 examples. There are around 54 strong, significant detections by LIGO Virgo, mostly binary black hole events. There are 2 events which are quite interesting from the EM perspective. The one, 1904-25, very convincing binary neutron star, and another one, 1908-14, which is a neutron star black hole event. This one was 150 megaparsecs, the binary neutron star, and the neutron star black hole event is around 270 megaparsecs. So in neither case was an electromagnetic counterpart found. In the binary neutron star case, half the sky was it was only one detector, and half the sky was in daytime. In the case of the neutron star black hole event, it could still be a low mass black hole event, and perhaps not involving a neutron star. That was quite a small sky area, which was observed in great detail by many facilities, and no one found a plausible counterpart. Let me just remind you of that signal on the bottom figure there, which shows time versus frequency. And this is the signal for 1904-25. So this is the only binary neutron star, convincing binary neutron star found in 03, released by the LIGO Virgo early this year. So let me just, I hope you can see the screen blinking here. So it's very impressive. You can just see, if you look here, so it's on, off, on, off. So this just blinks the before and after. So you can see that you can see the signal here. It's pretty weak. This is only one detector, and they identified this within 1 minute in real time and issued an alert, which is quite impressive to pull out that signal automatically in 1 minute. So one binary neutron star event in 03, which was at 150 megaparsec, right at the edge of their the horizon distance that they were sensitive to. So the next game changer, I think, so taking a step back and thinking about 03 and the efforts that the electromagnetic community made to get organized for 03, we had one binary neutron star event, one neutron star black hole event, convincing. There are other more marginal events, but these are the only two really convincing ones. I think looking forward to the next run from LIGO, 04 and 05, the next two runs, the fact that, look, they will come up with a better rate, volumetric rate for binary neutron stars and neutron star black holes after this run. But we know that we're probably not going to have more than, after the first three runs, we're unlikely to have many of these events within 100 megaparsecs. So in 02 and 03, we have one event at 40 megaparsecs and one at 150 megaparsecs. We're not going to get multiple events per year within 100 megaparsecs. Almost certainly the rates are telling us that. A number will come out very soon from LIGO, I think, on the volumetric rates. But just what we observed, we're unlikely to find in 04, when it starts up again, which is likely to be end of 2022, or sorry, start of 2022, end of 2021. And we're unlikely to find large numbers within 100 megaparsecs. So I think probably the next game changer in this field is likely to be LSST, because as what will happen in the next stage of 04 is that the sensitivity of all three detectors will increase by between 50% and a factor of 2 up to 05. So increasing the sensitivity by a factor of 2 will increase the rate by a factor of 8. Just goes with the distance cubed, of course. But they're likely all to be at the more distant extreme of the distance range, and so that puts them out of the detectability range of the smaller telescopes. So if you look here on the right-hand side, here's some simulations of what kilonova would look like at 200 and 300 megaparsecs. This is what I'm showing here. It comes from Raphael and Monguti and the Transient and Variable Star Science collaboration. This is the optimistic case where you've got a bright blue kilonova. And so you can see that typically it's only really Pan-STARRS and DECAM are getting these kilonova at 200 to 300 megaparsecs. All of these other smaller facilities won't make an impact if this, given that the rates are so low. In the least optimistic case, where these are red kilonova, which is being, it's really only LSST which will be able to discover them at 200 to 300 megaparsecs. So I think the next big game changer will be because we haven't really had the revolution that we might have expected if the rates had been higher. In 04, if as the distance limit and the range is pushed out by a factor of 2, the numbers go up by a factor of 10, but they will be out of the range of many of the smaller facilities. I think it will require LSST for that. Okay, so I'm just going to leave you one more thing before I summarize. I'm not going to go through it because I'm pretty much out of time. We've been searching for these kilonova without gravitational wave triggers, and to do this, we've been ingesting wide field survey data from we work with telescopes in Hawaii, the Atlas project and Pan-STARRS project, which we've worked with for many years. We also search the ZTF public stream. And so we collect all of this data in a data center in Queens. With the UK LSST project, we're going to make this a UK data access center. We're combining all of the public data that's available, plus the LIGO and the Virgo sky maps. We're going to integrate it with the high energy triggers from satellites as well. We haven't done that yet, but we plan to. And then provide a way for people to trigger facilities, mostly ESO facilities. We'll also, of course, then ingest the LSST data, combine this together, and allow people to search these catalogs in real time. We do all sorts of machine learning and cross-matching with catalogs to classify objects. And so we've been trying to search for kilonova without gravitational waves, because they should exist. Given the large range in rates in the nearby universe, we still have a reasonable chance of finding these even without a gravitational wave trigger. We haven't done so yet. We haven't found a kilonova. We have found one object, which we think is a white dwarf merger with a neutron star or black hole, but we haven't found a case yet where it's where we've identified a clear case where it's a kilonova type event from merging neutron stars. So I think I'm pretty much out of time. So I'm just going to skip to my summary. So these wide field optical surveys have changed the landscape of our discovery space. The physical powering processes are now, we can't explain this whole diagram just by powering through radioactive nickel-56. Probably magnetars or a central engine which is driven by black hole accretion likely drives the luminosity of many of these luminous transients. Stellar mergers are quite luminous. They play some role in chemical enrichment, but exactly how much remains to be seen. We need to understand what the rates are. I just ran out a little bit of time here. We have got this one event which looks like a white dwarf neutron star merger, sits in a similar range for the kilonova, but it's made up of the normal chemical elements that we'd expect in a white dwarf. It's not the R process elements. And so I think the next stage is really combining our detailed spectral models to determine the composition and the rates. And I think really for the next game-changing facility for electromagnetic follow-up of gravitational wave sources, it's likely going to be LSST, given that the observed rates from LIGO, Virgo in 03 were so low. We're going to have to search a larger volume, which means going fainter when we try and look at the electromagnetic counterparts. And of course, our ESO facilities in the UK are very well placed to do that follow-up. So thank you.
Thank you, Steve. Steven. Sorry that you couldn't hear